Hello there and welcome to the iRevised Supplementary Series for GCSE Physics. Today we're going to take a look at the Nuclear Physics Unit or Radioactivity Unit, whatever your exam board calls it. We'll take a look at isotopes, we'll talk about half-life, we'll look at a couple graphs, we'll look at uses and dangers of these isotopes, we'll take a look at a few nuclear equations, and we'll also have a look at talking about nuclear reactors, fission and fusion, and that sort of thing. Okay, so let's get on with things. All right, first up are some AQA questions. This is June 2017. This is paper 2. Name a substance that is used as a fuel in most nuclear reactors. I can't write in here, but I think we all know it's uranium. Okay, they're talking about plutonium-239 is used as fuel in some reactors, but most of them is uranium. Okay, energy is released in the process. Complete the sentence. Nuclear fission occurs after the nucleus of a plutonium-239 atom has absorbed a neutron. That's how most fission reactions will begin. And for the last 2 marks here, describe what happens when the nucleus of an atom undergoes nuclear fission. Okay, so you've got the nucleus of an atom undergoing fission. Make sure you are not saying we are splitting atoms. That's a very layman term. An atom includes both the nucleus and the orbiting electrons. We in nuclear physics don't care about the electrons. We are splitting the nuclei. We will split the nuclei into some daughter nuclei, some smaller nuclei, and also there will be some leftover neutrons, which will, again, propagate this chain reaction. I guess we'll be talking more about that later. Okay, mark scheme real quick. Yes, you can say U-235 if you like. Okay, I think uranium is good enough. Neutron, we said. Yeah, the nucleus splits. Do not accept atom splits. Do not say that, as we said. And you can have 2 or 3 neutrons ejected as well. That's fine. I suppose you could draw a diagram for some credit. Moving on. This is another AQA. This is June 2015, also a paper 2. What is nuclear fission? We can just say it's when a nucleus is split. When a nucleus splits. I'd leave it at that. Okay, we're, again, not splitting atoms. Okay, they're talking about nuclear power stations and whatnot up here. Plutonium-239 is sometimes as a fuel. What particle must be absorbed? Again, neutron. These I'm guessing these are very similar. I'm not sure what AQA's syllabus is, but we'll get into some trickier ones in a moment, I'm sure. Nuclear fusion is also releasing energy. It happens at very high temperatures. It's to overcome the repulsive force. Why is there a repulsive force between the nuclei of the atoms? Well, nuclei are positively charged due to the protons, so we need to overcome the electrostatic repulsion. That was what I would say. Where does the fusion happen? Naturally, in the sun, in stars. Okay, good, 1 mark. 3C, 1991, scientists produced the first controlled released from an experimental fusion reactor, and it was fusing isotopes of deuterium and tritium. Those are isotopes of hydrogen, by the way. Deuterium is naturally occurring and comes from seawater. Tritium can be produced from lithium. Lithium is also found in seawater. Okay, so we read all of this information because it might prove useful. And then they talk about the fission fuel and the amount of energy released. Okay, so from fusion fuel, we actually get, you see 10 to the 14, we get more energy released than the fission fuel, 10 to the 13. Don't let the beginning of this number fool you off. Look at the power of 10. So just 2 advantages of this fuel used in a fusion reactor compared with plutonium in a fission reactor. Well, obviously we can say right here from this information, more energy is released. It releases more energy. So boom, there we go. And then also we can get deuterium and tritium from seawater, and that's probably a heck of a lot easier and less expensive than getting it from uranium mines. And, compared to mining uranium, that can be quite dangerous and hazardous as well due to the radioactivity. And you got to, only certain countries have these uranium deposits, whereas seawater is pretty much everywhere. So I'd say the seawater, the fuel is readily available. That's what I would say. Let's move on. One last part here on this page, at least. Some scientists, by the year 2050, think that the nuclear fusion will be capable. So just one important consequence of developing nuclear fusion power plants to generate electricity. Well, they don't give off as much radioactive waste as nuclear fission power plants. So that would be my guess. And also, it's relatively sustainable because, you've got your ocean as your raw ingredients there. Last question here. Tritium is radioactive. Okay. After 36 years, only 10 grams remains from an original sample of 80. Calculate the half-life. Right. So what I would do is I would start with 80, and then I would draw my thing. I can't draw it, but you get what I'm saying. If I do half of 80 is 40, half of 40 is 20, and half of 20 is 10. So if you're counting on your fingers, that is 3 half-lives. And if you think about a half to the power of 3 is 1/8. 1/8 of 80 is 10. So there we go. We've shown our work, and we'll say the half-life is going to be, so if it's 3 half-lives we've gone through after 36 years, I would say our half-life must be 12. Right, so yes, splitting of the nucleus, do not say atom, neutron, we had said. Nuclei have the same charge. Nuclei are positive, they're going to repulse, that's right. They say main sequence star, except sun, except any other star, but it is a main sequence star. I mean, any two, this is for why would it be advantageous to do the fusion over fission? Well, very easy to obtain these materials from the water, available in very large amounts. Probably there's a heck of a lot more lithium and deuterium on the planet than there is uranium deposits. Releases more energy, we also said. Good. And little to no radioactive waste. Okay. Let's see. Naturally occurring is insufficient. Seawater is renewable is insufficient. Okay. Cost less, insufficient. Okay. Okay, so just be aware of this. They're a little bit picky on those. Those are kind of very wishy-washy kind of answers that are very likely going to be thrown out unless you really think about it. But yes, produces little to no waste is good as well. We had said more energy and easier to obtain. So there we go, and there's more of them. Okay, moving on, what's one important consequence? Well, makes another source of energy available, increases supply of electricity, able to meet demand, less environmental damage, reduces the amount of other fuels used. Any sensible suggestion, except in a specific example of that kind of stuff. I think we had said that it doesn't give off as much radioactive waste compared to fission. So that would be, I would say, less environmental damage. Okay. Try to be a little explicit. It's 1 mark, but you do got to get the point across. Okay, we said the half-life was 12. Good. Okay, moving on here. This is a WJEC, June 2014. This is a paper 3. Okay, so we've got a nuclear equation here. I am permitted to draw on here. So they're saying that in order for us to let's see, complete this equation. Well, we know they're both going to be hydrogen, and we need to have a total of 3 nucleons. So I suggest we have a normal hydrogen, the 1, and the hydrogen 2 is the deuterium. I think that's probably how that's going to work out. All right, part B, they give us another fusion reaction. This is what happens inside of a sun. Okay, so you get helium-3 with another helium-3 producing helium-4, which is the normal isotope of helium, and then 2 protons. And it looks like we've got a calculation here. Right, okay, so they're telling us that this might be a little bit advanced for some curriculum, but they're going to tell you the mass before and the mass after. We need to figure out what the mass defect or the mass loss is. Okay, so we're going to take this number here, we're going to multiply it times 2, okay, and that'll be the initial mass, and then our final mass will be the sum. Okay, we're going to have to multiply the mass of the proton times 2, and then we're going to add it to that. All right, right, so this times 2 is 6.029864, and I would just carry all those digits in. I'd save that number on your calculator. Hopefully you know how to do that. I'm going to take the mass of the proton, and I'm going to double it, and then I'm going to, I'll just write it down. So that's 2.0145, and I'm going to show for our marks that we're going to add that to 4.00151. And that's going to give us 6.01601. I'm going to save that one as well. And then I'm going to do that minus the other one. And the mass loss, I got a negative number here. I got 0.013854. That's the mass loss. That's the mass defect. And now they're telling you on page 2 to use an equation. I'm going to bet that it's E equals mc squared because they gave us C here. So, and that's the mass defect. So how much energy has been given off? Now what you see, we have to change that mass and convert it into kilograms. So we're going to take 0.01384 times 1.66 times 10 to the negative 27 times 1.66 times 10 to the negative 27. So that's a defect of 2.299764 times 10 to the negative 29. And we will multiply that. Yeah, E equals mc squared. We will multiply this number times c squared. And that's going to give us 3.32 times 10 to the negative 28 joules. It seems like a tiny amount, but this is only one reaction. And if you think of the 10 to the 23 or more of these particles, you know, you're going to be approaching a much higher amount of energy there. Moving on. This typical graph. Oh, WJEC, they love their written questions.
Right, yes. Using the graph to explain why energy is released in both nuclear fission and in fusion. Okay? It's a graph of binding energy per nucleon versus mass number. Sometimes you might see that as a proton number, but it's a mass number here. Okay? Just to remind ourselves what binding energy is, right? If I've got a nucleus, yeah, made up of protons and neutrons, if I were to try to pull one of these nucleons out of there, I'm going to have to do work against the strong nuclear force, which is keeping that nucleus together. So I'm going to have to do some work, and that work is going to be the binding energy, is what they call it. It's the amount of energy I would need to separate this nucleus into its constituent protons and neutrons. Okay? The opposite is true for fusion. If I've got a bunch of protons and neutrons and I wish to combine them together to make some sort of nucleus, there will be a change in mass, as we just saw up there in part B. Okay? And so there will be a difference in mass. There will be a mass defect. Now, there's still going to be a certain amount of energy needed, but in this case, because the strong force is what keeps it together, I'm not doing work with it, and actually energy will be released. I won't be having to put energy into it. And so either of these is called the binding energy. Okay, so explain why energy is released. Well, I guess we could talk about from what we just saw up above. We know about the E equals mc squared. We know that in a nuclear reaction, if there is a mass change, a mass defect, some sort of mass loss, then that mass is converted into energy. So we can mention that. Okay, and then let's talk about what's happening on either side of this graph here, right? So we know that fusion, you can fuse things more and more up until iron, and then from there you can no longer do any more fusing, okay? Because that's the highest binding energy per nucleon possible, and that's the most stable nucleon that you can have. Nucleus that you can have. Okay. Whereas with fission, we noticed that the constituent parts which would make up these two daughter nuclei, which could be theoretical. I don't think these ones will necessarily add up to give us uranium-235, but something along the similar lines. Daughter nuclei, when they are produced, they're going to have a higher binding energy per nucleon. And there's going to be a mass difference. When we are putting things together, this energy is released. Okay, so we can say when we break up that uranium into two daughter nuclei, that there's going to be a mass difference. And if each of these daughter nuclei have a larger binding energy per nucleon, they're more stable. Okay, what that means is we know energy is released when there is a fission reaction. And that energy that is released must come from this mass defect. Okay, so continuing on here, we know that there's a mass defect that changes into energy, and we know we could talk about fusion, we could talk about fission, we could say In both cases, energy is released because there's a mass defect. So I don't know. It says use this graph to explain why energy is released. I feel like we've done that, but I don't know if we're up there for the 6 marks. So maybe we can take a look at the mark scheme and see what they're going for. Okay, so we had deuterium and a normal hydrogen, so 1 mark. Oh, 1 mark each for those. Okay. We did the mass of the reactants. We came up with the difference. We got the mass of the here. I'm noticing that we've got some number problems, and I think what happened is when I doubled the mass of the 2 protons, my number should end with a 6, and you can see here, I neglected this 6, which would have made that a 7, which it's going to affect our answer there, isn't it?
Dick, I'm very disappointed.
I'm sure it's only a glitch. A temporary setback.
You call this a glitch?
2.0608 times 10 to the negative 12. Well, it's a lot larger a number. Okay, so we got we got the right answer there. That's fine. Well, we do now. So yeah, I missed one little digit there, and that created a whole thing. So just watch that. Right, so we talked about E equals mc squared, and that equates mass and energy. Binding energy is the energy equivalent of the mass difference between the whole nucleus and the individual constituent, protons and neutrons, or you could say daughter nuclei. Then they get talking about the graph. The graph shows that fusion of light nuclei into heavier causes an increase in binding energy. The product is more stable. In fission, the nuclei split into daughter nuclei with a higher binding energy. That fragment is more stable. So in fission and fusion, the mass difference is converted to energy. I feel like this first part and this bottom part are what they're talking about in terms of, explain how they both release energy. But I think there's more description in this question about what's actually happening with the graph, and that's when they start talking about a greater stability for the products of fission and fusion. Okay, so it's maybe a bit confusing here. It's a bit tricky because you might be tempted to think I need to talk more and more about this energy stuff, but I think there is enough part in this mark scheme in which in here they're actually just explaining what's going on with the graph. Definitely something for you to practice if this is included in your curriculum and your exam board. Okay, I've got another WJEC 2016 paper 3, June. Explain why our sun remains the same size. Okay, well, I mean, we did this in the astronomy video, but we can just say that the the gravitational forces are balanced by outward radiation pressure, something along those lines. Okay, to the next 2 stages in the life of our sun. Well, it's going to be red giant and white dwarf. Okay, now we get into the nuclear reaction, what's happening inside of the sun here. We need to fuse a certain number of hydrogens together to get helium. Now, it seems to me we'll need 2 of these, but see, we're going to have some electrons coming out as well. Let's see. Ooh. Well, for your nuclear equations, you know that a neutron can split to become a proton and an electron, yeah? This is your beta minus decay. Is that what's happening here? Because all of a sudden, look, if I put a 2 in front here, where do these extra 2 neutrons come from? They have to come from somewhere. Yeah? Is there something else going on here? Are we doing a proton? These all need to add up. We need to have conservation of charge. Now, see, an electron. Oh, do you know what? That's not an electron. That's not a beta minus particle. That's a positron. Otherwise, there would have been a negative in front there. So, the only way this is going to work, you put 4 hydrogens together. Does this sound familiar? Maybe you've seen that equation in your classes. Yeah, and 2. These are not electrons. Those are positrons because it's a +2. Okay, and that way we can get 4 nucleons up here, and then we can't just have 4 protons. We need 2 of them over here. Something else is going on, I reckon, because we're changing protons into neutrons. I imagine we're taking some electrons, and those 2 protons here are going to become neutrons, and then 2 other protons are going to be there. But we are only interested in the nuclear aspect of it, so I think that's that. We'll have to look at the mark scheme. Moving on here. This is a certain amount of energy produced by the sun. Calculate the mass loss of the sun per second. Okay. Each second, we are losing, 10 to the 26 joules of energy each second. So that's just per second. That amount of energy should be equal to a certain amount of mass times velocity squared. I reckon we just divide that number by the speed of light squared. So I get here a mass of 4.3 times 10 to the 9 kilograms. It's a huge amount. Yeah, all I've done is divided by speed of light squared. Let's take a look at the mark scheme. Right, so forces of gravity and radiation. Yeah, radiation pressure, that's fine. They're named, and we said they're balanced. Okay, so that's good. Red giant white dwarf. Good. We need to be in correct order. Yes, they do. What's this? 4 and 2. Yeah, so we had the 4 and the 2. There might be some other details as to why that works out, but that's the way it is. And then it was a 3-mark question. So I haven't shown it here, have I? I haven't quite shown it here. This is per second. I should have said that's equal to m times 3 times 10 to the 8 squared per second, and then I would have shown that I'm dividing, because you do get a mark here to plug that in, and then the manipulation. Without this bottom part here, I only showed the setup. I didn't substitute it in, and I didn't show the manipulation. Now, I know a bald answer typically is going to get you the 3 marks, but if you goof on your calculator, then you probably get nothing. So maybe just be a little bit careful about that. Okay, next I've got a OCR specimen paper, indeterminate year. Let's take a look here. Claire investigates relative penetrating power of different types of radiation. This is the apparatus, okay. And then they've got this experiment here. She's considering using a nuclear radiation emitters as tracers inside the human body. A radiation detector would detect them outside. Okay, here's the table. Decides alpha emitters should not be used as tracers. Why? Use the table, suggest why. Well, they don't penetrate very far at all inside that tissue, and if we're going to be tracing and then having these coming outside, it's typically they use gamma for that, don't they? Maybe beta, depends. So we can just say alpha has too low a penetration. It's not going to go. You're not going to detect it. Okay. What would be the other thing? It is highly ionizing. And alpha particles, and since they're very highly ionizing, that could be a problem. But it does talk about using information in the table to suggest why. So I would say they don't have a very good penetration. I'm not sure what they're looking for, and I don't have a mark scheme for this. So either they're looking for, well, obviously gamma has better penetration, so we would want to use gamma. Gamma is better. Okay, or maybe you might say, hey, alpha has got high ionization properties, and that could be a problem inside the patient. Although that's nothing to do with the table. I might suggest alpha's too low, gamma's better. Part B, and this is the end of the question. Claire uses a small amount of radioactive material and then it must be disposed of carefully. Okay, so what are some ways of disposing radioactive waste? Well, we can do a lead case. I think sometimes they put cement around it. We bury it underground, and maybe you might put some sort of badges or something to kind of warn if the radioactivity is still present, that kind of thing. But I think that's okay for 2 marks. I don't have a mark scheme. My apologies. Okay, let's move on here. We've got, here you go. This is your dice experiment. Let's get through these ones fairly quickly. Predict how many dice would show a 6 on the first throw. Well, they have 600 dice, and it's a 1 in 6 chance, so our prediction should be 100. Okay? State why we cannot predict which die will show a 6, because it is a random process, and the whole reason we use dice is to illustrate that it's random. We have no better way of knowing which die will roll a 6 as to which of these atoms is going to decay. Okay, now let's take a look at this table here. Obviously, we need this number to be between 85 and 60. And you might be saying to yourself, well, look, this dropped by 10, and so maybe this is 75. But then it's 10, 10, 10, and then 5. And you might think, well, if I went up from 60, I'd be at 70. And you might be tempted to say to yourself, well, I'll put an answer somewhere between 70 and 75. I'll put in 72. Okay, and you might think that. Okay, but let's take a look at what actually is going on in this table here. If I look up, I count here, I go 30, 40, 50, 60, 70, 85, and to get to 600 is 95. Now if I look, 95, and if I look, oh wait a minute, that's the 95, the 85, this is the 60, 40, 50. So this distance here was 70, this answer must be 70. Okay, so you're using all of the table to come up with this. This is just the number of dice remaining, and you're going to remove them each time. If you've done this experiment, it's very obvious. Hey, I got 95, I take them out. How many are left? 505. Okay, 85 take away, I got 420 left. Now I take away 70, and I got 350. So 70 is your answer. Okay, now in this case here, they're going to ask us to plot a graph. Right, draw lines on your graph, and then what you do is you draw yourself a nice one smooth curve. Can I make a suggestion to you that a lot of people will start off at the top and try to make a curve down? I'm going to suggest that you start down here and draw away, and you've got far more control. I kind of messed it up there at the end. You get far more control from drawing away from the end, because your pen can control going outward better than you trying to draw it in this way. That's just my experience. Don't draw these kind of sketchy lines. Don't draw up to here, then you miss and then start over. Don't do that. It needs to be one continuous smooth curve. All right. And what's the half-life? Well, we can do a couple calculations here. We'll take our line 400. And 400 is just a little bit there. It's at 2.2. And then we'll go down to 200. And 200 from our line, I mean, my curve here isn't the best. It could be up higher. But I'll take it where it hits 200. And that's here at 5.8. So if I do 5.8 minus 2.2, I get 3.6. Let's try something different. Let's take that 5.8 from the 200, and from it we'll subtract what? Oh, we don't hit 100, so we can't do that. Obviously, background radiation hasn't been taken into account. Shall we try something different? Let's try 300, and that takes us to, looks like 3.6, and then we'll go 150. 150. It's a bit tricky on the computer. It's about 7.1, 7.2. I suppose it's 7.15. I don't know. We'll say 7.2. And it looks like, 3.6. Let's say 3.6. They'll give us a plus or minus. Oh, don't forget your decimal. They'll give us a plus or minus, I'm sure. Americium-241 as a radioactive substance, and yeah, if you've learned about your smoke detectors, yeah, why is it radioactive? Well, the why is anything new? The nuclei is or are unstable. That's why they're radioactive. And what's an alpha particle? It is a helium nucleus. Okay, you can write the whole word out if you like, but that's fine. Explain why we use it in smoke alarms, and it's not a health risk. Probably because it's got a long half-life. We want a long half-life because we want it to work in our house for a long time, and so if it's got a very long half-life, we can say it's got a low activity, a low radioactivity. Okay, but then also because of its low penetration, it's gonna hit the wall of that plastic, and it's not really going to go anywhere. Okay, so we can say stopped. the housing of the device, something to that effect. Let's have a look at the answers. Okay, 100, it's random, yeah, good. Right, okay, so 70 for B, right, on the table. For the plots, within plus or minus a small square division, -1 mark for having it wrong, and a smooth curve best fit plus or minus 1 small square division. Okay, now my smooth curve maybe wasn't the best. I'm on a tablet, so it's a bit tricky, but this probably could have been a little bit better. What's the half-life? Horizontal and vertical lines. So you get a mark for drawing on your graph, like I was showing. Draw those lines in for your calculations. Now, what do they get? They get half-life taken from the intercept of their graph, around 4. Half-life. We would have subtracted. We got 3.6 on 2 different calculations. They say 4. Don't demand horizontal lines to be drawn when there are major. Allow answer close to 4 where no construction lines. I think we would have gotten it. Allow answer rounded to whole number. Well, we did look. If you've done your construction lines here with a nice, and I'm being sloppy, but you grab a ruler, pencil, draw some nice lines, show the calculations. We're close to 4. I'm assuming we got the answer. Okay. And imbalance between. Accept. They will tell you to accept unstable nucleus. We said nucleus. But really, that is what's going on. It's the imbalance between protons and neutrons. If you remember that graph, where they've done neutron number versus proton number, the zone of stability kind of, down for light isotopes, it's a 1-to-1 ratio, but as you get higher, it's a 1.4 to 1 ratio for stability. So it's an imbalance between protons and neutrons is a better answer, but that's what makes the nucleus unstable. And you have to say nucleus. Don't just say it is unstable or the atom is unstable. Okay? Don't talk about electrons. Too many neutrons, not necessarily the problem. It's the imbalance between the two. Okay, so yeah, they can get a little picky. Just be aware. Right, we said a helium nucleus. You could have said an alpha particle was 2 protons and 2 neutrons. That's fine. Right, what did they say for the last one? Why would we use americium here? What did they say? They said alpha particles have low penetrating power. Ooh, I said low penetration. I'm not writing a full answer out like you should be doing, though. And we've only said low penetration. We should have said, hey, this has low. No, it's not the americium that's got low penetration. It's the particles that are released in radioactive decay, which is the alpha particles. So now I don't know. You'll have to go back and watch the video. Did I say alpha particles have low penetration? Maybe I said that and I didn't write it. Your job is to write it. Okay, you need to say alpha particles have low penetration, and therefore they can't get through the plastic. They can't get through the air. Okay, so they can't get through the housing of the device. Okay, not to do with a long half-life. They haven't mentioned half-life anywhere in here, so maybe don't bring it up. I think we've only got one there. All right. Oh, what's this? Alpha is highly ionizing. Alpha can't travel far in the air. Oh, you could say that. That's fine. Neutral answer cannot get through the skin or pay. Yeah, it's not going to hit you, but it's a better answer to talk about the alpha particles. Okay. Yes, I've got another dice experiment question here because it's a WJEC. It's a January 2015 paper 2. This is a little bit different though. It's more of an experimental type slant to begin. They tell you a whole bunch of things at the beginning. In the interest of time, you can pause and read them on your own. Each group, you guys know how the experiment works. One reason why the bigger sample size makes the data more repeatable. Well, if you've got some anomalies, because it's very random, it could be you get some really high or very low comparisons. What this will do, this will, let's say, smooth out data or any anomalies on the graph. Because, of course, remember, we are going to make a smooth curve. So we don't want any fluctuations. We don't want to, we want it to be kind of smooth. We don't want points making it kind of jagged like a stock market. Okay, so I would say that that's fine for 1 mark. Let's move on. Okay, now they're going to want us to plot a graph again, aren't they? All right, I've plotted my points. I'm going to draw that graph. I'm going to, like I say, start at the bottom here, and I'm going to smoothly draw it. That's not bad. That's okay. I got a bit of a squiggle there at the beginning, and I missed that one. Okay, so what do we got here? Use the class results to find the half-life. Okay, so, we've started at 400. Let's go down to 200. I'll switch colors here. 200, that's going to take us down to, it's 3 away from the, so that looks to me like a 3.7. So we gone from 0. So I'll say 3.7. Let's try a different half-life. We can get as low as 100. Let's take that 200 and we'll draw another 100 over to here, and it's gonna come down. You're gonna of course have a pencil and ruler. It'll be a lot better. Okay, so I've got a 7.2. Well, 7.2 minus 3.6 gives us 3.6, but minus 3.7 is going to give us a 3.5. And I think if we were to average this all out, if you've got time later at the end of the test and you want to check some stuff out again, try something else. Let's do 300. That takes us to about, let's see, 1, 2, 3 squares away. So that seems like a 1.7. And we'll go down to 150. And that seems like a 5.2. 5.2 minus 1.7. Yeah, that's the 3.5, isn't it? So we're all kind of in that area, 3.5, 3. I'm going to write 3.6 again, just because I got a 3.7 and a 3.5. We'll see. Hold on. Now use the graph. Okay, so for my graph, it's 3.6. Use the class results. I suppose if we were to start at, say, we've got 400, and we want to get down to 200. 200 somewhere in between 3 and 4, isn't it? 200 somewhere in there. It's 10 away, and this was a difference of 40 between these two. So it's 10 away from 200. So if I split that up into quarters, I'm guessing 3.75 is what we would get. Could we try a different way of doing it? Let's start at the 280. How far to get down to half, which is the 140? Again, 140 is in between, but this is just a difference of 30. So it's like a 2/3 kind of thing. So I would suppose we're going to start at 2, and we're going to get in somewhere between 5 and 6. And I would say 5.6. 5.6 minus the 2, and I'm at 3.6. So again, it's somewhere between 3.6 and 3.7. 5. I would probably say 3.7. That's from using the class results. We'll have to look at the mark scheme. Right. Why is it better to use a graph than a table? Well, it's just easier. It's just easier to visualize. It's easier to visualize and remove anomalies. Remove anomalies. We'll see what they say. Use your graph to find how many rolls it took for the number of dice to fall to 1/4. Well, if we had 400, we'll go down to 100. We can compare those. What was this? This is a 7.2. So 7.2. And again, it took 7.2 rolls, and that's basically, we can say, hey, that's 2 half-lives, isn't it? Because we had said it's about 3.6. Okay, and it matches it. I couldn't just say it's 2 half. It matches with 2 half-lives of our calculated half-lives. Let's see if that's good enough for what they want. Okay, an experiment was carried out. Beta emitter, the initial count rate was measured to be 80 counts per second. After 210 seconds, it had dropped to 10 counts per second. So that's 3 half-lives, because that's a half to the power of 3, which is 1/8. So that's 3 half-lives. Find the half. So 3 half-lives, right? So we've got 3 half-lives. So 210 divided by 3, I'll say 70 seconds. Okay, calculate how long it would take for the count rate to drop from 80 to 2.5. Well, it would be just a little bit longer then, wouldn't it? If we've got 10 to 5 is another half-life, and then a 2.4, so that's 5 half-lives. So if a half-life is 70, okay, then I guess it'll be 5 times that. It'll be 350 seconds. Maybe the other way you could do it is you could say, hey, I'm at 210 seconds. Okay, and I need to do 5, and this 210 corresponded to 3 half-lives. What's it going to be for 5 half-lives? Yeah, and if you do the math here, that's 70 times 50, so I think we got it. State the unit of activity. It is a becquerel, CQU, okay, or the symbol I'm sure is BQ. Becquerel is not capitalized. Okay. Let's look at the answers. To smooth out random fluctuations, variations, reduces the effect of anomalies, something along those lines. That's fine, okay? It's okay to say less anomalies or weird results. Don't say it prevents. It doesn't prevent anomalies, okay? It's not more accurate. It's not more reliable. It's not more accurate, okay? There's other ways to increase reliability and accuracy. This question is about why we use the class. This is why we use a bigger sample size. Okay. All right. I'm sure we did the plots fine. That's okay. We got all the points. I'll let you pause and read the rest. About 4 rolls, anywhere between 3.6 and 4. What did we say? Number of rolls needed. We went and did some calculation. As we had said, you could have just looked at, hey, look, from 400, I need to get to 200. It's somewhere in between here, so it's somewhere between 3 and 4 rolls. I'm sure you could have said that as well. Okay, so somewhere between 3 and 4. Our method from the graph, okay, 3.8. That's a bit high for us, but we had said 3.6. Okay. They're going to give us a plus or minus 0.1. One value taken from the graph. Plus or minus 0.1. Oh, darn. We said 3.6, and they're only going to give us up to 3.7. Again, my graph, this curve could have sloped out a little better. Maybe I could have done a better curve. Maybe my lines here. It's tricky for me on the screen here. So it's tricky on a tablet, not on a piece of paper. But there you go. But if you show what you're doing, and if you're close enough, you might get the 2. What was this question about? Why is it better to use a graph? It allows more precise or accurate values to be obtained. To near of a roll. Graph is more don't accept exact value. It's not the exact value. A graph allows us to be more precise or accurate. What did we say? Easier to visualize, remove anomalies. Yeah, that's not a good answer. Wants us to be more precise, they say. 7.6, I think that's what we hit. Well, 7.2. Ooh. I'm going to check that. According to our graph, down to 100. Well, I suppose if my graph had curved a little better here than the 100, then the 100 would have came over a little bit. And the 100 would have been, 7.7, 7.8. I can see that. So my graph was not the best. With these half-life graphs, it really should go through every point. It really should be possible. So I was off a little bit. They had, so 7.6. We had 7.2, so we didn't get it. Okay? Don't just take a quarter of the original value. Okay? Or don't write that. You need to actually calculate it from the graph. Okay? And we did say it's approximately 2 half-lives, so we get a mark for that. We were just off on the value, unfortunately. We had said 70 seconds. We had said 350. Yeah, we had done those calculations correctly. That's fine. Okay, don't just write this stuff down without saying, hey, that's 1, 2, 3 half-lives. Each arrow you draw is a half-life. Don't just write that down. Okay, becquerel, you can write BQ, capital BQ, any reasonable spelling, but just don't spell becquerel with C-A-T. Okay, let's take a look at some IGCSE Edexcel papers. This is June 2015. I think all of these are paper 1 I'm going to be doing. Right, so here you've got a nuclear reactor, and they're asking you what's the process, the splitting process. Well, that's fission. And the control rods, you know about the control rods, they control the reaction by absorbing some of the neutrons. Okay? Right, that was a very straightforward question, but you can see here from the June 2016 that they like the same diagram, but in this case, they're asking you to match things up here. So we need to take a look at how things work. So what absorbs the dangerous radiation? That would be the shielding. What contains uranium for fission? That's the fuel rod. And the coolant removes energy from the reactor. All right, moving on. State the type of energy released. It is kinetic energy. Kinetic energy. Just do that. Remember that, okay? A lot of students have a problem with this. It's kinetic energy. The particles have a lot of energy and they're moving around, and that's the heat energy which causes the steam to evaporate and so on, but it's kinetic energy. The role of the moderator in the fission reaction. It slows down neutrons so they may be or can be absorbed by our fuel, okay? And then the fission process happens. Okay, explain in terms of neutrons what is meant by controlled nuclear fission. Now, sometimes there'll be a question like this, and it'll be to talk about a chain reaction. This is about controlled nuclear fission, okay? So we can say that each fission reaction releases more neutrons, okay? Each new neutron, I'm not going to write this all out just in the interest of time, but we can say each new neutron causes new reactions. Okay, we can control the number of reactions. The number of reactions by control rods which absorb neutrons, and then those neutrons don't go on to cause other fission reactions. And we can just say that it's the fission. So the energy, there's energy created and released, but it's never too much that it's uncontrollable. Okay, something along those lines for 3 marks. Okay, so we've got that pattern correct. That's fine. Kinetic energy. It slows the neutrons down. You can say it reduces the kinetic energy of the neutrons, which allows fission to continue. It allows the fission to occur so the uranium can absorb the neutrons. What did we say? Slow down so they may be absorbed. Okay, but absorbed by what? Absorbed by what? Ooh, they're tricky on that one. Underline, absorbed by neutron. Okay, and then the other question here. Okay, so any 3 of these, okay? Basically, what have they said? Yeah, so each fission is caused by a single neutron, and that releases more than 1 neutron. I believe we had said that. And then excess neutrons can speed. So if you've got too many, we'll have an increased rate of reaction, and then that's excess energy, which we don't maybe really need. And so we got control rods to absorb and regulate. And that's kind of what we had said. I'm sorry, I kind of rushed through that. Okay, moving on. This is June 2017, and we've got a nuclear reaction here. What is meant by fission? It is splitting of nucleus. It is not the atom, it is the nucleus. Calculate the number of neutrons released during this fission reaction. The number, okay, so we got to balance this out. So we need 92 here. 56 and 36 is 92. We need a total of We need a total of 236 neutrons here. By my count, we get 234 if we add these. So I think we need 2 neutrons. Okay. Explain how a chain reaction can occur in uranium-235. We can say 1 nucleus, not atom, 1 nucleus splits, releases more neutrons, and each I won't write it out, but each neutron can therefore go on and that's in this according to our reaction here, that's 2 new neutrons being made. So each of these 2 new neutrons will go on to cause other, and it's like 2 to the power of n number of times that these collisions go on. And so you can see it kind of grows exponentially. But basically, yeah, one nucleus splits, more nucleon. Basically, one nucleus splits, more neutrons, I was in the middle of saying created, and then each neutron causes further fission reactions. That's basically the idea. With reference to the equation, what is meant by the daughter nucleus? Oh, well, I mean, we could just say that the barium and the krypton are daughter nuclei. They're smaller versions of the original. Well, not, I guess we wouldn't say smaller versions. They are smaller isotopes. They are different species. Okay, so I would just write them out by name. I would say barium and krypton are the daughter nuclei. They are the products left over besides the neutrons. And barium-144 is a radioactive isotope, emits beta particles. It's used as a tracer. Sometimes explain what happens when it emits a beta particle. Okay, well, we had it up above there. Barium was the 56, if I'm not mistaken, and 144. And when it emits a beta particle, you know that a neutron is changing into a proton to create that electron. And we're actually going to have what will actually happen. Because what happens to the mass number? Nothing. Nothing happens. This barium will cause this beta decay will cause one neutron to become a proton, and we will change into a new element. It won't be barium anymore. But we can say because talk about this because the mass of protons and neutrons in our syllabus in our world, in our GCSE world, are basically the same. Even though you can say, even though a neutron's changed into a proton, because the electron has no mass, the mass number stays the same. Okay, so we said a nucleus splits. That's what fission is. Using a conservation of nucleons method. Yeah, so we got 2. That's fine. So however your method is, that's fine. You got 2. One of the released neutrons is absorbed by another uranium nucleus. That's the part I missed out. We said each neutron can go on and cause another fission reaction, but we actually explicitly need to say it needs to be absorbed by another uranium nucleus. Okay, and then that will release more neutrons, and there'll be more and more and more, and then each neutron is released, is going to be absorbed by another uranium nucleus. Don't forget that part. Yeah, barium and krypton, we had said those are the daughter nuclei. Oh, okay, you just got to name them. That's the daughter. That's it. Allow symbols. Good. Okay, and I guess the other point, they are formed during the fission. Okay, that's fine. These were created during the fission. That's a daughter nuclei. Okay, and then a neutron changes into a proton is what happens with a beta decay, and the mass nucleon number is the same, so it's constant. That's pretty straightforward. These GCSE questions are these Edexcel questions are quite straightforward, aren't they? Here's another one. So non-ionizing, ultrasound is non-ionizing. All the other ones are ionizing. Okay. Okay, next, give 2 precautions doctors should take when using ionizing radiation. Now, I started writing this, and I was writing it from a patient's point of view, but let's look at this. 2 precautions that doctors should take when using ionizing radiation. I was talking about dosage. I was talking about the half-life, if it's left inside of them. But we're talking about that the doctors need to take. Okay, so they might wear protective lead. Don't just say, protective lead vests. Don't just say protective clothing. Talk about them being lead lined. Okay? Maybe limit exposure time. Maybe you and the other doctor can swap off doing treatments every other week or throughout the day. Limit exposure time. You don't want to be dealing with that stuff all the time. And then, of course, safe storage, that sort of stuff. Okay, so our diagram was correct. That's fine. We had said keep exposure time short. Also, maybe keep distance exposure as long as possible. Wear protective clothing. Oh, you don't even have to say like just protective clothing. What a silly thing. I never understood the thing about goggles, because if you've got, I guess goggles will stop beta decay, but they're not going to stop gamma decay. I had a lot of students saying you should wear goggles when dealing with a gamma source, and I just thought it doesn't really make sense because they go through anything. But I think protective, I would say lead-lined clothing, because you never know. Maybe one year this isn't good enough. Okay, store sources safely, and that was a bit vague of mine. I could have said store in a lead container as well. Right, moving on. This is January 2014, and they've got a question here. This is their version of. Right, okay, so this is January 2014. This is a paper 1, and they've got their question regarding some experiment here. And you've got your count rate per minute, corrected count rate. So it looks to me like they've subtracted 30 from the background. State 2 sources of background. This is, yeah, you definitely need to know 2 sources of background radiation. We can say space. A lot of people might say rocks underground. And this is where the radon gas seeps out from. I think that's fine. There's probably a few other sources, but let's look at the marks at that later. Describe how the scientists should measure the background radiation and correct the count rate readings. 3 marks. I would measure count rates without the radioactive source, in several locations. Obviously, you want to keep the time constant for whatever you want to do, okay? Several locations, and then you're going to take an average. You're going to calculate the average, and then you would subtract your average count rate, which is your background now, from the other readings. That's what I would say for 3 marks. Let's have a look. Oh, plot a corrected graph. I think we've done enough of these. That's fine. I'm going to suggest watch your scale, watch labeling your axes. This is going to be activity versus time, and your graph should look like. And you get marks for how you plot your point. 5 marks. We'll look at the mark scheme, and we'll also see. You guys know we've done enough of these now. How to figure out? You do the time for 1, and then you figure out what half of that is, and you subtract those 2 times. That's how you get it. We'll take a look at the mark scheme in a moment. Okay, so real quick, sources of, background radiation, rocks, radon gas, cosmic radiation, I guess medical sources, nuclear waste, some foods, there's a radioactive isotope of potassium in the bananas, so sometimes they'll have that. I think rocks, radon gas, radiation, that's fine. From the sun or from space, that's fine. Okay, remove the radioactive source. We said measure the background rate. We're going to repeat the measurement. Background radiation is 30. Subtract. So we said to subtract. So you don't have to give a number. They said how. They said how should they do it. They never said it was specifically going to be 30. But I think we got the gist of that there. Okay, and then your graph should look like this. So corrected count rate. So you are not graphing the counts. You are graphing the ones that have had 30 subtracted from it already, and your graph should look like that. Okay, how did they get? So 5 marks, different than some of the other papers we've seen. You got a scale. You want your graph to be at least half the page. This is perfect. Axes are labeled. Good. Some exam boards do that. Some don't. Plotting to the nearest small little square and your line of best fit. And as I said, it's always nice to maybe draw away. Okay, evidence that you've used your graph. So 400 down to here, and then 200, and then you make your subtraction and the correct value. And Edexcel is really nice. They'll let you get a certain range, won't they? Okay, so maybe you tried that at home and got something. Okay, well, we'll continue on with part B. The radioactive nuclei is a source of beta. What does the emission of beta? What effect does the beta emission have on the nucleus? Well, okay, we know a neutron is changed into a proton, and in order to get this beta particle, this electron, to be ejected, so the mass
is constant. The mass number is constant, but we're actually going to create a new element. We're going to have create a new element because we'll have a different number of protons. We'll have a proton number +1. I would say, hey, we're going to gain a proton, new element. We need to reduce the risk when working with radioactive sources. Why can they be dangerous? Okay, so it's kind of similar as before. They can ionize. DNA molecules. They can cause mutations. These mutations lead to cancer, something along those lines. Describe how the risks of working with sources can be reduced. Okay, 3 marks. Okay, so again, very, very similar. Limit exposure time. Yeah. Do not, direct contact, no direct contact. So you're going to use gloves. Yeah, we talked about protective clothing, lead-lined, that kind of stuff. I'm just... to get this done quickly, I'm not going to write it all out. You don't need to see me write it out. What else? Oh, protective badges. Protective badges, which show when you've been exposed for enough time. That sort of thing. Let's look at the marks. Right. Correct statement about a neutron. Neutron changes. Neutron is going to decrease by 1. Correct statement about a proton. It's going to increase by 1. That's all you really need to say. What's going to happen to the atom? Yeah, well, proton number goes up by 1, neutron number goes by down. That's a little bit obvious, and therefore the mass is the same. Allow 1 mark for nucleus becomes another new element. That's if you haven't said either of these. It's only 1 mark, though. I guess to be real specific, we've said that the proton number increases. I don't know if we explicitly went out and said the neutron number decreases, so make sure you do that. Okay. What are some dangers? Well, they emit ionizing radiation. That's what we said. That's the first bit, and then any one of these. Can't be seen, so you don't know if it's being hit at you or directed at you, or can't be seen, so you don't know if it's directed at you or if you're in danger. It can harm or dangerous. It can cause cancer. It can harm or dangerous. Mutate cells. Sure, I'm fine. Okay. Any 3 suitable. Okay, so you can reduce exposure time. Handle with tongs. I was going to say, yeah, keep distance. You can get these things where you get these gloves that are inside of another room and you can work on stuff there. Shielding, fume colored, wear your badge. That's fine. Gloves and masks are considered shielding. Use shielding. That's fine. Okay. Allow, keep it. Yeah, so store it. It's kind of what we saw before. That's fine. Okay, and then this is June 2014. There is a number 11 here, and it's got an equation that we need to sort out. I think we had seen before that this will be 56. And let's see, we want these to add up to 236. And there's 3 neutrons, so that's 145. We want 236. So it looks to me like that's going to be a 91. Explain how nuclear fission can lead to a chain. Okay, so now here's the chain reaction question. We can just say, one nucleus, don't say atom, one nucleus splits, releases more neutrons. And this is what we had, this is the thing we need to say, just like before. We can say each neutron, let's say, splits. Oh, no. Let's not jump there. Let's say each neutron is absorbed by another uranium nucleus, and that causes further fission, another split, and then each step releases more and more neutrons, something to that effect. Nuclear reactor question, yes, again. Label the control rods and the shielding. Okay. So here is the shielding. Okay, this. And the control rods. Okay, so the uranium rod is here, this gray thing. And I would imagine that the control rods are these. This is going to be difficult to, but it's these black rods, because you can either pull them up or push them down, and they will stop. They'll stop the neutrons from whizzing around in there. Okay. Explain why the shielding is needed. We can just say something along the lines of to prevent, escapee
neutrons from causing damage to contain this radiation. Okay, let's have a look. Okay, we were correct about 91 and 56. That's good. Neutrons are released. Neutrons slowed by the moderator can be absorbed by other nuclei, causing further fissions. Oh, interesting. Ne3 from... I didn't mention about the neutrons being slowed by the moderator, but I know we talked about that before. I said, hey, neutrons are released. They'll be absorbed by other uranium nuclei. Again, bold-faced, so say nuclei, causing further fissions. That's fine. But you have to realize in order for this to happen, the neutrons are ejected very fast, and so they need to be slowed down in order to be absorbed. Okay, but there you go. So if you know a little bit of these steps, you can, 3 marks out of the 4 things you could say, that's fine. Correct labels, yeah. We got the control rods and the shielding. Any part of the control box, black in the diagram. Any part of the external box for the shielding, good. Okay, and then here, reactor material or waste is radioactive. It ionizes and causes, and it's penetrating, and it causes issues. Okay, do you know, prevents escape of radiation. To prevent, I said escapee neutrons, but I suppose there's radioactive material in here as well, which is releasing radiation. I guess radiation is being released, whether it comes from the neutrons, which as I've said, or whether they're talking about the waste inside. Either way, that doesn't matter. You need to get into saying, hey, what does shielding do? It stops radiation from leaking out, okay? Meaning radioactive waste, radioactive decay, whether it's the neutron or whatever. But basically, it's going to prevent ionizing of cells and tissues, and it needs to be done because it's very penetrating. It needs to be thick, lead-lined concrete and that sort of stuff. So again, watch the vague wording, because sometimes they're looking for other things, aren't they? I've got a question 12 here as well, and these are they love this diagram. You're going to see it everywhere. It's just another matching question, isn't it? Okay, so what absorbs neutrons? That's going to be the control. What absorbs neutrons? That's going to be the control rod. What slows down the neutrons is the moderator. A lot of students get these confused. Don't do that. The fuel rod contains the uranium. The reactor vessel and the coolant. Well, the coolant is going to transfer thermal energy, and the vessel is going to keep the radioactive material inside. Okay, I'm sure that's fine. Which of these is a product of fission? Neutrons. All right, the process of nuclear fission. Let's talk about one thing that I think a lot of people forget, is that in this case it's the uranium nucleus. It will absorb a neutron. Okay? And that absorbing of the neutron makes it unstable because of this ratio of neutrons to protons. Okay, so I don't want to call it the new nucleus, but it kind of a way is, because if you've got uranium 235 and it absorbs a neutron, it's going to become uranium 236, isn't it? Okay, so the new nucleus is it's unstable, and so it splits. It's going to create daughter cells and release more neutrons. These neutrons, in turn, get slowed down by the moderator, and then they get absorbed by new uranium nuclei, and the whole process repeats. Something to that effect. We'll look at the solutions in a moment. State 3 ways in which fission differs from radioactive decay. Well, I would say radioactive decay is random. We never really know if that's going to happen, whereas with fission, if that neutron gets absorbed because it's traveling at the right speed, you can pretty much guarantee it's going to happen. We can control nuclear fission. We can't control radioactive decay. Radioactive decay, at least the ones we've been talking about, typically we are only ejecting beta or alpha particles, whereas with fission, we are ejecting neutrons, but we also get these larger daughter cells. And what else could we say? I would say that
usually nuclear fission is not spontaneous. It's something that we cause to happen, whereas decay happens through nature. I'm interested in the marks. Let's see. Yeah, so we got the right line crossings from that. C was neutrons, product of fission, and then they were asking about the fission. Yeah, and there we go. Neutron is absorbed by the uranium nucleus. It causes it to split. I think we've already got 3, and then it's going to create daughter products, daughter isotopes. Ooh, don't say daughter cells. I've seen a lot of students say daughter cells. I don't know if I accidentally said that a moment ago, because with mitosis you get daughter cells, and I think some students get confused. Okay. Oh, and then releases neutrons, releases more neutrons, we said, and energy. Okay, so I think we're okay. We got that, but know that process. Know, and like sometimes you can say 5 or 6 different things, and maybe on 1 mark scheme you need to say 3 of them. Maybe you need to say 4 of them. Maybe 1 mark scheme they won't give you credit for saying causing it to split. Who knows? So make sure you know enough details. And let's see, 3 comparisons. Decay is random. Fission is not. We said that. Fission induced by input particle, but decay occurs without input particle. Yeah, you have to bombard, you have to shoot a neutron at a particle. That's kind of what I was saying in that we make it happen. It's something that we induce. Okay, we have control over. That's kind of what I was getting at, but I don't know if that's enough. Okay, we have to shoot a particle at this fissile material, they call it, and then it'll undergo fission, whereas decay just happens whatever. Fission produces daughter nuclei, but decay only produces 1. Oh, okay, 2 daughter nuclei. Yeah, if you fission, you split, you'll get your 2 daughter nuclei. It is a nuclear reaction in which we are changing, with a beta decay, for example, or an alpha decay. We're just changing the number of protons, and so we will only have 1 daughter. Okay, so that's good. A little bit below what I was thinking, but that's a very simple answer you can give. And what's this? Alpha or beta are emitted from decay, but not from fission. Oh, yeah. The only thing emitted from fission is neutrons. Alphas and betas are emitted from radioactive decay. So that's another fairly straightforward one there. Okay. I think I probably only got to 2 out of 3 there. All right. This is a good question so that you can understand not only what is radioactive decay, but what is fission. And comparing and contrasting similarities and differences is a great way of studying. Right, that takes us to nearly an hour again. Time certainly flies when you're having fun. I hope that's been helpful for you. Make sure you're practicing your written work. Make sure you know your steps. These types of questions can be very easy to master with enough revision of past papers. Take care. We'll see you next time.